History of iron hypothesis. A theory that contends the availability of iron restricts the growth of phytoplankton in the ocean of the planet. The, the idea first surfaced in the late of 19th century when scientists researching the ocean ecology noticed regions of the water were rich in nutrients. In 1889, John Martin suggests that the absence of iron in some oceanic region could be the cause of the lack of phytoplankton, as this would encourage their growth and enhance their availability to absorb carbon dioxide, hence reducing the consequence of climate change. In 1993, in a large experiment, Martin and his family introduced iron to a football field-sized area of ocean water in the Southern Ocean. The experiment strongly supported the iron theory by demonstrating an increase in phytoplankton growth, and carbon dioxide uptake. Since then, the iron hypothesis has become widely accepted within the scientific community and has led to increased research on the role of iron in ocean ecosystem. Main objective of iron ocean fertilization. By introducing iron to the ocean, a geoengineering technique is known as ocean iron fertilization is used to promote the growth of phytoplankton, which use photosynthesis to absorb carbon dioxide from the atmosphere. Main objective to increase the amount of phytoplankton in the ocean in order to reduce atmospheric carbon dioxide, which will lessen the effect of climate change. Discovery of atmospheric gas composition in the ancient time. John Martin, who proposed the iron hypothesis, did not directly study the atmospheric gas composition. Instead, he used information from studies of ice cores to infer change in atmospheric gas composition over time. Ice cylinder called ice cores are taken from glaciers and ice sheet. This layer of ice, which has built up over thousands of years in this core, provide information of historical climatic condition. Martin was interested in how the amount of carbon dioxide in the atmosphere was changing. Scientists have used their hypothesis regarding the function of iron in the growth of phytoplankton to explain how the quality of carbon dioxide in the atmosphere varied over this time period by analyzing ice core from Antarctica. Martin suggested that a shortage of iron during times of high carbon dioxide concentration, such as during the Ice Age, was what prevent phytoplankton from growing in the ocean. He proposed that introducing iron to these locations would promote phytoplankton development and boost atmospheric carbon dioxide absorption. Location of iron fertilization experiment: Southern Ocean, Equatorial Pacific and the North Pacific. First, the Southern Ocean, largest HNLC region in the world ocean. First performed in February 1999 for 13 days. Next is EISEN EX was performed in November within an Antarctic polar current eddy in Atlantic sector to test how atmospheric dust might lead to dramatic increase in ocean productivity. Next is to see the outcome of iron and silicate. Two ocean iron fertilization experiment were conducted in January-February 2002 in the Southern Ocean Iron Experiment North, SOFEX and South SOFEX S. Okay, in March-April 2004, another experiment was conducted by SOLAS in sub-Antarctic waters. A was carried out during the austral summer of 2004, around 39 days than experiment before. Next is the Hafez experiment was conducted in January-March 2009 for 40 days, where iron added to a patch of ocean water about 300 square kilometers. Okay, Subarctic North Pacific. SEED 1 was conducted in July-August 2001, around 13 days, in western subarctic gyres. Next, SEED 2 experiment was conducted in 2004, around 13 days, in the western North Pacific, where iron was added to an area of about 100 square kilometers. Next is series was performed in July-August 2002 within 25 days in the Gulf of Alaska. Lastly, this result showed that iron addition lead to an increase in phytoplankton growth and carbon uptake, indicating the potential of iron fertilization as climate change mitigation strategy. Okay, next is Equatorial Pacific. The iron EX1 was conducted over 10 days in October 1993. Next is iron EX2 was conducted in May 1995, and was investigated for a longer period, around 17 days, which giving more information about the biochemical, physiological and ecological response to the ocean iron fertilization. There is 4 hypotheses to the weak response. First is the possibility of unforeseen micronutrient and macronutrient. Next is the short of residence time of bioavailability iron in the surface patch due to the colloidal aggregation or sinking of larger particle containing iron. Next is insufficient light brought by subduction of the patch. Lastly, high grazing pressure of zooplankton. For subarctic North Atlantic, the experiment was conducted by European Iron Fertilization Experiment. The experiment was conducted in 2004 and involved the addition of iron to a patch of iron in the subtropical North Atlantic. The result showed that iron addition lead to an increase in phytoplankton growth and carbon uptake. Okay, next is the relationship between iron and carbon dioxide in atmosphere with the growth of phytoplankton. First, phytoplankton are tiny, single-cell organisms that live the upper layer of the ocean and undergo photosynthesis. Next is in some area of the ocean, iron concentration are low, which limit the growth of phytoplankton. When the iron is added to these areas, it can stimulate the growth of phytoplankton, which can absorb carbon dioxide. When phytoplankton die and sink, they bring along the carbon and sequestering it in the deep sea. When the iron is added to the ocean, it can increase the growth of phytoplankton, which can lead the reduction of the amount of carbon dioxide in the atmosphere. And lastly, when iron is limited, the phytoplankton growth is limited. Okay, next is experiment ocean iron fertilization. Law effects to investigate the impact of iron fertilization on phytoplankton growth and carbon sequestration. The results were inconclusive, with some suggesting the amount of carbon sequestered was low than expected, and the bloom did not have significant impact on ecosystem. Okay, second, seed to investigate the impact of iron fertilization on the growth of diatom. The result showed that added iron had a positive effect of growth of diatom, but did not lead to significant increase in carbon sequestration. And lastly is sulfates. The result showed that added iron had positive effect on growth of diatom, but did not lead to significant increase in carbon sequestration. Next is limitation of the experiment. As compared to the extent of the ocean, the experimental patch were small, making it challenge to apply the finding to broader areas. And the study were carried out in several places under various environmental conditions, which may have had an impact on the outcome and limited the comparability of the data. Next is our comprehension of the long-term impact is limited by relatively short time frame of the experiment. And lastly, the possible environmental risks of the iron fertilization were not really investigated in the research. All ocean iron fertilization experiment achieved its main aim and considered as success. Okay, first, the result of experiment have been mixed, with some studies showing that iron fertilization can increase the growth of phytoplankton and lead to carbon sequestration, while others have found limited or inconclusive result. Next, when phytoplankton die and sink to the ocean floor, some of carbon they have uptake is sequestered, but some of it is also released back into the atmosphere through respiration by the other organism in the ocean. Lastly, additionally, there are potential risks associated with iron fertilization, such as potential of harmful algal bloom, and it is not yet clear how effective and feasible iron fertilization is as a long-term solution to mitigate the effect of climate change. How to improve ocean iron fertilization experiment in the future. Okay, first, experiment design. Larger experimental patch, longer time scale, and more constant environmental variable should all be included in future OIF trial in order to solve their shortcoming. Next is ethics and regulation. To avoid any negative effect on the marine environment, OIF investigation must be carried out ethically and in accordance with environmental law. Next is international cooperation. Okay, international cooperation is essential to coordinate OIF research effort and ensure that the study is conducted in a collaborative and transparent manner. This could include establishing global guidelines and standards for OIF experiments. Next is monitoring the data collection. It is essential to collect accurate and comprehensive data during OIF experiment to evaluate their effectiveness and assess any potential risks. Monitoring should include measuring phytoplankton growth, carbon sequestration, and change in ocean chemistry, as well as assessing the potential ecological impact of iron fertilization. Lastly, long-term evaluation to assess OIF experiment effectiveness and climate change as a climate change solution. Long-term evaluation is required. This entails taking into account the likelihood of feedback loop and unforeseen outcome, as well as the method scalability and viability.